Okay, so following on from just some knowledge sharing channel that I did, I think it was last week or week before, there were some questions about how do we use these tools and how do we actually find these problems in the first place. So the example I posted, and I couldn't reproduce it last week because my laptop wasn't plugged in. So pro tip, make sure you're plugged in and laptop's not under thermal stress, because otherwise all your numbers will be thrown out. So the problem I had was it performed badly even if I applied the fix. And that's just because the laptop it was on power saving mode. So it throttled my CPU. So tip number one, when you're doing performance testing, make sure you've got a consistent baseline. So when you're doing Octopus as well, make sure you turn off your tasks. So go to your nodes tab and drain the node, so you don't have the background tasks kicking in inadvertently. Helps out. So I was working on the infrastructure page and I did some performance improvements on the overview. So now, as you can see, it loads all right. And in this case, I had 1,000 machines, 1,000 tags, and 500 tenants. So whenever you're making new changes to this aggregate data, I really recommend loading up your machine with that kind of level of data, with maybe 1,000 tenants and 1,000 environments, and distribute the machines and tenants across the environments and across tag sets. So if we look at the setup, I've got tenants. They've each got multiple tags, and each of the machines has, there's 800 machines in this particular tag, so almost everything is in the first few tags. And then just a nice kind of random distribution, essentially. And that way I found I got, at that scale, I got a lot of the n cube problems, where 1,000 deployment tags plus 1,000 tenant tags means 1 million things happen, right? Anyway, I was working on this and I clicked through, I saw how quickly the screen was working now. It was much better than before. But then I came in and clicked tenant tag, and this screen took ages to load, or much longer than I expected. So I thought I'd have a look into that. So I break out LinkPad and use the API, because I found the performance numbers inside Chrome are not quite as accurate, because it includes some processing time of the return JSON. So through this, I'm just going to run the summary overview. So that's getting a summary of everything across the system. And that runs in 677 milliseconds, roughly, 666 milliseconds, right? And then I'm going to run the same summary, but only filter it down to the tags. Now, in theory, this should take less, because it should take a lot less deployment targets into account when it's doing its calculations. But I found it takes about 1.6, about 1.6 seconds. Note, I'm actually running it under not under the debugger, or because that also adds a little bit of time and a little bit of instability to the numbers. But I found that if you run it from a console, it runs quite evenly. Okay, so I want to start looking into that. So I'm going to close this and I open up this awesome tool from JetBrains called .trace. I think a lot of us have a license for it. I think it's come through. We all have a license for it, yeah. So I choose the application to debug, Octopus Server in this case. I add my options, run this demo. And I'm not going to start immediately. Now, I'll go through each of these first three options and why you would use them. So always usually start off with the sampling one, which is accurate measurement of call time. So if something's running slow, we're going to find out where it's running slowly. So I'm going to run it. So let it start up. I'm going to run the test once, just to warm up the system, because I'm not really concerned about the first time run. I'm concerned about the next 300 times this API runs. So the first time it runs takes 1900, and the second time is 1600. The difference is usually something to do with caching of JSON transformations, warming up all our statics and everything, with the web layer. Because this is the first request that hits the API at this point. As you can see, this particular tracing hasn't added much to the actual call time. So I'm going to start the analysis. I'm going to run it again, and while it's running while it's under kind of the analysis, a little bit more time is added. So there's maybe extra 20%. So I finished. Now I'm going to get the snapshot of what happened between the time I hit SNAR and get the snapshot. And it's going to load up, and then I'm going to kill this process because I don't need it anymore. So here's the snapshot. This out of the way. And now I just got to find the actual thread that handled my request. So it's one of these two because it's an unnamed thread for web. So looking down, there it is. That's apply filters to machine. The summary responder. So I can see that's the thing I want. The other one is probably my login that I did earlier. Oh no, it's a service status responder because I should close that so that I don't get any interference from the actual polling from the website. Anyway, so I'm looking down at this and I'm looking at where my hot path is. So I would start with this thread ran for 90% because the threads are kept around in a thread pool, so they don't get killed, but they're not actually doing work. So my first callback is only 10%. 1.6 seconds, which kind of matches up with my with the time I got back in Linkpad. I can right click on it and just zoom down into that particular call. So I can go open current method instance, and now it goes to 100%. So now I'm thinking, okay, this is the request all the way down. So 100% is the request, and now I'm going to just hit the right arrow and just zoom down into where is actually all this time being taken. So there's all this stack around Nancy, et cetera, and here is where it really starts to fragment into different times. So again, I'm going to isolate my analysis to that particular method. And in this case, it's a summary responder. So this is the thing that responds to and builds up our response. That's where our performance problem is, 1.5 seconds of it anyway. And interestingly, it's split across these two items. The one I'm going to look into today is this first one, the apply machine filter the machines. And again, I'm going to go into that just so I get my headspace that this is the only thing I'm looking at. So I see, okay, there's 100, yeah, okay. On the right-hand side, I can see the code that's being run. It highlights it for me. So apply filters to machines is this whole method. And then there's a to list. So which is this thing down here. And then there's this inner method that's taking up 932 of milliseconds. So almost all the time is spent in this particular line of code, which is quite interesting because it doesn't look like it should spend that much time there. Based on, there's a whole lot more code up here, right? So yeah, so digging in, we're looking at, okay, it looks like this contains function this function here is taking a lot of time. And then I thought, well, actually, hang on, wasn't I just in here? Why am I suddenly in over here? And that's important later. Okay, so I've kind of pinpointed down where the actual problem is, which is block of code. So I want to do another analysis, which is a line by a tracing analysis to see what magnitude of problem I'm dealing with. So again, I'm going to run it, go through this quickly. Yep. Heat up the system. And this kind of tracing, it makes the program run a lot slower. So you're not going to get accurate time out of this, but you'll get an accurate measure of call count. Yep. Okay. 18 seconds. The second one should be quicker. Yeah, 5 seconds. Okay, so I'm going to start the tracing. Six seconds, yeah. Okay, cool. Wait for the analysis to load. Okay, again, I'm going to go. I know where the problem is now, so it's in the apply in-memory filters. So I can Control F. I just did there to go and do a search, and here we go. So I'm going to open that instance, zoom down into it. There's only one call to it. That's all I've got from the API. Again, I'm going to zoom down and see. Okay, look, we got 23,000 calls. That's not too surprising. 200,000 calls here. That's getting a little bit smelly, but that's still not a huge amount. So we got, yeah. But again, I'm questioning why is it calling this particular line 200,000 times? It feels like it should be calling it once per tenant, right? And we don't have 200,000 tenants. So I'm kind of marrying up my expectations of the complexity of each of this method against what the tool's telling me. I look down into the contains method and I find that this equals is getting called 10 million times. I'm going, oh God, okay. And that's this, but that must be this contains that is comparing this collection to see if this thing is inside the collection 10 million times. Like, okay, right, I think we got our smoking gun here. The line by line, I'll probably skip over that actually. Okay, I'll skip over the line by line one. It'll just give you a lot more detail about how many times each particular line executed. And again, not a very good measure of call time. So I'll go and look at the code now and make some changes. So the first change we're going to make is here, this contains method, like this is getting called 10 million times. So I'm really going to optimize that. And I'll find it's a list. So I've got a list of strings, and that's, we should really be using a hash set or a reference collection here. So a reference collection is a hash set with a invariance comparer, string invariant comparer. So casing doesn't matter when you're doing contains. Good, that's fixed up. Good old resharper or writer has gone and told me possibly unintended linear search in this set. So what this means is I've used this overload, which overrides the comparer in the hash set. So it's going to do a search top to bottom instead of a hash search. So, and hash searches are, if you remember your maths, is log n. So as the number increases, it only gets logarithmically larger, whereas a linear search is linear. It's a straight line instead of a line like this. So I'm going to remove that comparer because it's redundant. Okay, I'm going to build that. 6, that build, it's building. There we go. Okay, and I'm going to run it up in my server just from the console, and I'm going to, so what was our number before? 1.6 seconds, wasn't it? So I'm going to run it again, and 1.2 seconds for the first time, and 700 milliseconds for the second time. So that's also already a great thing. So I might leave it there, but I could have left it there, but I'm just going to fix up why is this getting called 10 million times? And that's because this is an enumerable. So it's a lazy loaded collection, and we're using that lazy collection inside another loop. So for every machine, we're evaluating this collection over and over and over again. So by throwing a to array on the end, we allocate some memory, but it's a lot more performance. So allocating 10,000, an array of 10,000 items is not even noticeable on the profile at that time. So I'm going to compile that, and let's see if how much improvement we got in here. Good, one instance. Yeah, okay, a slight improvement. If I took that hash search out, if I took the hash set out, it'd perform in about the same time anyway. So the combination, either one of those would fix the problem, but I'm just going to add the to array there anyway because it doesn't cost me anything. The code's just as easy to understand, if not easier to understand. So I'm going to leave it there. Lastly, I saw that there's the new tag tenant tester, and I want to move that out and only create this once because it looks like for each tenant, all we're doing is creating a tenant tag tester for each of these. So I'm going to create one just once, dot select tenant tag tester, and then this is tag testers, and whether the machine applies to tenant with a tag tester in there. And shorten that off. So build that. Now, yeah, it's this optimization isn't because the creation of the actual object is expensive, as in the allocation of the CLR object. But if we look into what it actually does in the constructor, is it does some aggregation. Away. Anyway, it does some aggregation of the data, sorry, what's the word? Processing of the data, and that does take some time. Yeah. So getting rid of the thing, building that. Good. Okay, run her up. And then test it again because I could have inadvertently tested each time because I could have inadvertently made it worse. So there you go. But in this case, it's better by 40 milliseconds. 40 milliseconds probably isn't something that's worth looking into, but while you're in the area anyway, you might as well change it while you're testing it. Right? So the last thing I want to show is how can we get a better idea of where we've improved in performance. So I'm going to run the sampling scenario again. Where is it here? Zoom's in the way. Run. Can quickly run through the scenario. Yeah. Okay. Start capturing 5. What have I done? I ran the wrong one, didn't I?
I think it was on tracing instead of sampling, Rob.
Yeah. Oh, yeah. Thanks. That's why it took so long to start up. Yeah, that's better. Okay, start 5. Snapshot. I'm going to open up the new snapshot and one of my old snapshots. So this one I did, so it's sampling, yeah. Let's go. And in both snapshots, so I've already got my apply to machines filters zoomed in there. My new snapshot, I'm going to do the same thing. Apply to filter machines. Look, and that's great. Look, it's gone from how much? 932 milliseconds to 15 milliseconds. So that's great. So there's not much more we can do there. But you can click this button here. Oops. Is this Zoom being zoomy? This is Zoom being zoomy. Hang on a minute. Nope. Here we go. Try this button. Compare snapshots and choose the other snapshot. And now we get a diff between the current snapshot and the old snapshot down to each method call. I saw that, okay, we've got an extra call to extra time spent in applies to tenant, but it's pretty trivial. Most likely it's just moved from in the tree as well. It's moved from here to here, basically, this particular call, just because we reordered the code. Yeah, so that's it. So download the tool, give it a go, look at the timings of your calls and see if you can fix them up for us. Any questions?